Okay, this is a quick recap of what we covered in our last couple of science lessons in Year 11, looking at topic 2, electricity in current in circuits. So here we have a simple parallel circuit with two resistors. They could just as easily be bulbs or any other components for that matter. And I have a cell at the top here. You can see the direction of conventional current has been labelled on this circuit diagram with an arrow showing an anti-clockwise flow of electrical current around this circuit. And we should now remember that an electrical current is a flow of charge, and that in most electrical circuit situations that's going to be a flow of charged particles in the form of electrons, which are negatively charged themselves. Because electrons are negatively charged themselves, that means that if a conventional current flows from positive to negative in the direction of the arrows shown, then the actual direction of electron flow is opposite to that. So they leave the negative terminal of the cell up here and pass through the circuit in the opposite direction before returning to the cell at the top. We then had a look at how we measure current, and current is measured with an ammeter, and an ammeter is a component that must be connected in series. If a circuit itself is just a series circuit, that means it contains just one loop, so one way of passing through the circuit like this. Then the current is the same everywhere, as the current is a flow of electrons. As long as none of those electrons can escape, and in a circuit there is nowhere that can happen, then we can account for those electrons in every place in the circuit. They will all be here, they will all be here, all be here, and so on back around to the cell. If it happens, like in this circuit I've got here, that I have two possibilities for the electricity to follow, two pathways, first of all through resistor 1 and then back to the cell, and secondly through resistor 2 and back to the cell, then I can have a current that splits up where it meets the junction here. So let's say, for argument's sake, the total current here is 10 amps. It'll get to this point here, and quite possibly 5 amps of that current will flow through resistor 1, and 5 amps of that current will flow through resistor 2. If I add up those two currents, so that's I1 and I2, then I'll get a total of 10 amps still, which shows me that the total current is still constant. Those two currents will rejoin on the right hand side of the circuit at this junction here, combining back to make my total 10 amp current in this simple circuit. If we then go on to consider voltage, we describe voltage in a really basic way as the push that makes the current flow, and in a more complicated way, the energy given to the flow of charge. I can measure the energy difference between 2 points in a circuit with a voltmeter. They get connected in parallel. I can measure it across my cell, and my cell will tell me how many joules of energy I give to each coulomb of charge based on its voltage. So 1.5 volts means 1.5 joules per coulomb of charge. Now I'm putting that energy in where the cell is, and I'm going to take it out in the other components in the circuit. If this were a series circuit with just one loop, then all the energy would be lost through resistor 1, lost to heat. And so I would have a voltage across resistor 1 of the same as I had at the top. If it was 1.5 volts here, it would be 1.5 volts across resistor 1. Because this is a parallel circuit, then effectively what I've got is I've got the second loop still connected to both sides of my battery. This has the effect of increasing the current, thus increasing the rate that energy is given to the circuit, and it allows me to have the same voltage across R2. A circuit like this, with two identical components in parallel loops, will simply mean that the battery will run out twice as quickly as it would if there were just one loop. If I'd actually got two resistors next to each other in a series loop, so we're going to ignore this loop here for the time being, if I've got one here perhaps and one here, then the total voltage across both those two would be 1.5, the same as my cell voltage, and across individuals it would be half that voltage if they were identical components, so 0.7 volts across each one in that case. If they were non-identical components, then the voltage across each one might be different, but they would still add up to the 1.5 volt total voltage, or total electromotive force, if you want to use an A-level term, from the cell at the top. And that pretty much covers what we've done in our last two lessons.